In this video lecture, we will explain how to relate map views to cross sections. This means that we will purposefully match up actual locations on maps with the underlying strata, or rock. Anytime we go to the trouble of matching a top view with the side view underneath, and we do that exactly, we call it a cross section. So here's an example. This is the map view. Red indicates divergent boundaries and the black lines indicate transform boundaries. First off, can you tell me how many distinct plates there are in this map? I see 1, 2. 2 plates separated by both divergent in red and transform in black boundaries. You'll notice that these oceanic boundaries, divergent boundaries, are offset by these transform boundaries, okay? This is incredibly common that your ridges, your mid-ocean ridges, are actually separated by transform faults, and that happens because the spreading at any ridge is not necessarily going to be the same speed of the spreading at the adjacent ridge, and so it requires these transform faults to take into account those differences in speed of different ridge segments. So, given all of this information, let's go ahead and just systematically add everything that we know onto this map video. Go ahead and pause the video so that you can sketch the above geometry into your notepad and work along with me. On your sketch, make sure to leave some extra space in the bottom for more sketching later. All right? Okay, go ahead and pause it and write this in your notebook. Okay, at this point, we're ready to start. The first thing that we want to do is to draw in the relative plate motions of these two different plates. So we kind of already started, but this time we're going to do it systematically. We're going to start at the mid-ocean ridge. Anytime we draw what's happening at a mid-ocean ridge, we're going to start our arrows on the ridge, and then the plate on one side is going off to the direction, and on the other side, the other direction, okay? So I'm just going to add little arrows like those to all of the boundaries because it's important that every single boundary have an arrow. Okay, now that that is done, I need to go back in and draw in the arrows at the transform faults. It's actually easy to mess up the transform boundaries. So the one way to not mess up is to just make sure if this part of the plate is going this way, everywhere on this plate must be going this way. So if we start at the ridge again, but this time just draw our arrow super close to the transform, then we'll have it going the right direction. So it should look like this. Okay? And because these arrows are a little bit wonky, let's go ahead and clean that up a bit so you can see what it would look like with a smoother hand. Okay, so here it is just a little bit clearer. And you should see that I have diverging arrows going from every divergent boundary and arrows indicating the transform boundaries as well. The next step is to add the volcanoes. We know that mid-ocean ridges, oceanic divergent boundaries, are volcanic, right? They have lots of volcanoes. In order to sort of indicate that on the map, I'm going to draw in some triangles. Let's see, I might change my red in the hopes that maybe these triangles will show up a little better. There we go. So every triangle just means that I recognize that there are volcanoes all along these ridges. And there we have the completed map view diagram that includes all of the relative plate motions on either side of every boundary, along with all of the volcanoes. Okay, great. Now that that's done, the next thing that I want to consider is, what does this map view look like right at that location of that purple line if I was to look under the earth there, right? Like if this was a cake and I made a slice down that purple line and then I looked in the side, what exactly would I see? If I figure that out, well, the answer is the cross-section. So I had to make my image a little smaller to make sure that I could draw in the cross-section under the picture, but hopefully you left room on yours. Okay, the thing about cross-sections is that they need to match the map view perfectly. So that means that when I start on this side, I need to start with just oceanic lithosphere. When I get to this feature here, it had better be a mid-ocean ridge. And then I have just oceanic lithosphere all the way to the end of my map. Okay, let's try. So now that my computer is down on my desk like a piece of paper, I can draw my cross sections. So there's one of my 2 oceanic plates. It goes all the way to the edge of the map. Very important, right? It has to match the map view. And then it has this mid-ocean ridge in the appropriate location. And the other side is going to be another oceanic plate all the way to the end. Oops, that's a little bit skinny. The end of the map. You know, I don't like that line, so we're just going to redo that. Bottom one more time. That's better. Okay, now we better add a couple of arrows to show that it's a divergent boundary, and we are going to go ahead and label the mid-ocean ridge as always. Okay. Here is a different map view. This time there are 1, 2, 3 plates. Remember, it's common for continental and oceanic lithosphere to both exist on a single plate. It's plate boundaries that represent locations where plates move in different directions on either side of the boundary. And that's what makes a plate boundary, those differences in motion leading to these ridges and trenches and volcanoes. The simple change in composition from oceanic to continental, that does not cause a boundary to occur. Why don't you take a second to pause the video, sketch this new configuration into your notebook, and then go ahead and attempt to draw in both the plate motions and the resultant volcanoes on your own. You might feel like you don't know what to do at first, but just go ahead and give it a try. Again, you are going to draw in all of the appropriate arrows and triangles for the volcanoes while I go and try to make my dogs be quiet. Okay, now that you have all of your arrows and triangles drawn onto the map, I'll go ahead and walk you through how I do mine. Okay, just like before, for the mid-ocean ridge, we're going to start on the ridge and draw an arrow pointing away to indicate these are locations that rocks are moving away from, diverging. For the transform, we're going to do the same thing, except right up next to that transform fault. And for the convergent boundary over here, we need to draw arrows pointing in towards that boundary, because this is the direction those rocks are moving at that location. So now that we've got our convergence, divergence, and transform arrows drawn in, we need to figure out where the volcanoes are. Let's look at the mid-ocean ridge first. So as you remember, the mid-ocean ridge is an undersea volcanic mountain range. So I'm actually going to draw little triangle volcanoes all along that ridge, okay? Now, there are also volcanoes associated with subduction zones, which is what this oceanic continental convergent boundary is. This here is the trench, so I'm going to actually go ahead and write that in there. I actually don't recommend that you write yours on the bottom. If I were you, I would write yours up here at the top. That'll just make things easier for you a little later on. And this one here is the mid-ocean ridge, which we abbreviate MOR. Okay, back to these volcanoes at the subduction zone. Do you remember where they go? Volcanoes are always on the overriding plate, and at an oceanic continental convergent boundary, the overriding plate is always the continental plate. And so we need to draw those arrows just a little bit inland, but parallel to our trench, like so. Okay, now as you could probably guess, we're not just going to stop after completing this map view. Instead, we also need to add a cross section. Go ahead and pause this video to try drawing in the cross section on your own before letting me explain how to do it. Even if you just attempt to solve it on your own and you don't actually get it correct, it will still help you figure out how to do this the next time. So go ahead, pause the video. Did you get it? Let's see. Like always, we're going to start at the edge of the map and draw in this oceanic plate all the way to the mid-ocean ridge. And then to that subduction zone. Finally, we have a continent. And it looks like I didn't leave enough space for my little volcano, which should be over here. And one change that I could have made, I could have let this continent sort of go like that. Let's see here. Oops, the whole thing disappeared. All right, I'm going to do it for you one more time. Comes in like this, up and funny shaped continent, but this way it agrees with our map. Okay, now here's our trench, mid-ocean ridge, and it looks like that is all that we need. Almost. We also need to remember to put arrows on all of these plates. Oops. Wow, that one was a little wonky. I'm going to redo that. There you go. We have our convergent boundary and our divergent boundary, and they all agree with the map view. We have all of our features labeled, and we have arrows on all of our plates. So now we should be good. At this point, hopefully you're starting to feel comfortable examining a map view and picturing the side view in your mind. You should also have a general sense of where on the planet each of the various boundaries are and be able to select them from a map. For example, can you identify a pair of locations characterized by oceanic trenches? Pause the video so that you can take your time to think through the problem. Instead of jumping straight to the correct answer, we'll look through all of the options, starting with A. So, boundary A here is out in the middle of the ocean, so chances are it's probably a mid-ocean ridge, not a trench, okay? C, hard to see in the video, but also most likely a ridge. Now D here, okay, well we've got ocean right next to land, and if you know anything about Alaska, you might know that this is actually volcanic arc, okay? So D looks like it might be a good guess for a trench. F, down here, the western coast of South America, well, I happen to know, and you can kind of see here, that in addition to just being ocean right next to continent, which is a good sign, there is indeed a trench at F, and this line here, this topography, those are the Andes Mountains, which are volcanic, right? So we have everything that we would expect: a trench and a volcanic mountain range and an oceanic plate right next to a continental plate. And this answer is actually correct. The pair of locations that both have trenches from this list is pair DF. Okay, well, let's go ahead and go through the other options anyway, just to make sure we're getting this. B and E. Well, if we look at B, there's no oceanic plate over there at all, right? This is actually a continental collision zone, which is creating these mountains, some of the tallest mountains on planet Earth. And over at E, well, this boundary is pretty complicated. Part of that is a transform fault. This is where the San Andreas is. And once you get more over here, it's actually a subduction zone. So that one's complicated, and that could have been a trench, but because we had continental collisions over here, we know that 3 cannot be correct. Finally, G and H. All right, well, G, once again, middle of the ocean. So what is that? That's a ridge. That's the spreading center. That's oceanic divergence. And H, same thing. Once you develop an understanding of these boundaries, you begin to comprehend why there are volcanic eruptions in Washington State, but not in Indiana. Why there are large earthquakes in California, but not in Florida. Understanding the basic principles of plate tectonics will enable us to explore these dangerous phenomena and ultimately determine what, if anything, can be done to mitigate them. This concludes the map views and cross sections lecture. See you next time.